All right, people on Zoom, can you guys hear me?
Yeah.
All right, let's take a quick review. We started chapter 4b last time. And that's the equation, that's the K equation we learned, work energy equation. All right, first, you should remember this equation. It's a not very hard equation to memorize. And when you write out that equation, make sure you write the equation correctly because it's very easy to put this work down from non-conservative force to the other side. But keep in mind, this work down U and C must be on the side with T1 and V1. All right. And we talk about how to, what are each terms. T is kinetic energy, V is potential energy, and potential energy could come from different types of potential energies, such as gravity. Weight force will give you potential energy. Spring can also give you potential energy. We talk about what is the work done U and C from 1 to 2. That's the work done by non-conservative forces. And one example of non-conservative forces would be friction force and external forces. Then we talked about the steps in this chapter, in this section. Okay. From my observation yesterday during my office hours, and I've realized one thing. When you guys write out your homeworks, you don't label the steps. I didn't see that on your homework solution, but I require you, you must label each step from step 1 all the way to step 9. All right, I know it's tedious, have to write that every single time, but believe me, that could help you to make sure you don't miss any steps. Make sure in your homework, in your exams, label each single step. And if you have time, make sure you label what is each step is for such as FBD or set up coordinate system, stuff like that. But in section 4B, we have 9 steps. So that's a lot of steps. But the first 5 steps are exactly the same as chapter 4A. And the new things starts from step 6. It's building tables. Building tables for kinetic energy, building tables for potential energy, and the last table is the work done by each conservative force. So once you have 3 tables, you can use that 3 tables to assemble your work energy equation, to plug in everything for V2, T2, T1, V1, and work done. So that's what we learned last time. Any questions on those 9 steps? Once again, it is required on your homework and exams, you must label each step and you must create tables like we did here. Okay, that's a requirement. All right, so today we're going to get into details to look at specifically work done. Okay, I prepared several cases. You're gonna tell me what is a work done. Okay, last time we reviewed what is work, how to calculate work. Anybody remember how to calculate work? Hunter?
Force times distance.
Force times distance. Okay, keep that in mind. That's a basic equation to calculate work done. But it can be tricky sometimes to find the correct work done. All right, the first case we're going to look at here is pretty simple. We have a ball with mass m. If we apply a force F to this ball. And this ball is going up to a certain height. Now let's say we apply, instead of a force, we give this ball an initial speed. Right now, at position 2, the ball has a new height. Let's call that h. What is the work done? Who did the work? In this case, can we draw the free body diagram for that ball? How many forces on that free body diagram? Everyone? How many forces should be on the free body diagram? 2? What are 2 forces, look?
One force of gravity pulling it down.
Mm-hmm.
Force that's pushed it up.
Okay. If we don't have a ball, but imagine if you grab a ball, just give it a initial, just throw it into the air. And what is the, do we have a force pull the ball all the way up? Let me just like, let's throw my pen. At the initial point, I may give a little bit force to add that speed. But once it's in the air, how many forces we have? We only have one gravity force pulling that ball down, right? So in this case, the work done for that ball is all come from that mgh. So gravity is doing the work. So in this case, it's a exchange of kinetic energy and potential energy. If we call this position 1, this position 2, at position 1, we have the ball has only, if we set this point as zero potential reference. Remember last time we mentioned potential energy depends on where you set up the reference point, right? So at position 1, the ball only has kinetic energy. At position 2, once the ball hit the maximum height, it only has potential energy but zero kinetic energy. Did I say that wrong? This one only has kinetic energy but zero potential energy. Okay. Now let's look at another case. If we have a box, and we have a smooth surface, we apply 2 forces on this box. One force is going down. Let's call this F1. Another force is going to the right. Let's call that F2. And this is a smooth surface. So this is at position 1. At position 2, the box is pushed to this new position. Let's call this position 2. And the distance here is called L. So which force? We have 2 forces, F1 and F2. Which force will do work for this case? Spend 1 minute, talk to each other. Which force would do work? Is that force 1, force 2, or both of them? Yeah, 0 reference point. Okay. Let's do a survey. How many of you think F1 would do work? Raise your hand. Think F1 would do work? No? How about F2? Okay. All right. So what's the work done from F2? Let's call this U. The work done from F2, from position 1 to position 2 equals what? F2 times the distance that force the mass is traveled. So just F times L. Okay. If you want to write out what is work done from F1, that is 0. So F1 does not do work. So here I want you to make notes. If a force is perpendicular to the path or to the motion of the particle, and that force would do 0 work. So F1, it's a perpendicular. To the motion. And therefore F1 does 0 work. So any forces that has a direction perpendicular to the motion of the particle, and it only does 0 work. Okay, now we had the third case here. We have a path start from point A to point B. So we have a particle that can move along that path. And the particle, the force applied on the particle, it's F. So this F force has a constant direction and magnitude, constant direction. Which means the direction of force is only pointing to the right. It doesn't change. And we know the length from A to B, the direct length from A to B is L. The distance, if you calculate the curve, the curve distance from A to B is SAB. Okay. Now I want to ask you, what is the work done by the force F? So the work done from A to B by F, what is that work? Should that be force times L, or it should be force times SAB?
It should be L.
Should be L. Why is L?
Because since it's going in a constant direction, it's only ever going to be on the L plane, not the SAB, because SAB goes downward at some points.
Okay. How many of you agree with him? It should be F times L. Raise your hand if you think it's F times L. Okay. Raise your hand if you think it should be F times SAB. Okay, I will hold the answer. Now let's talk about another case. Case number 4, same thing, we have the same curved path A to B. We have the same particle. Now the force, how we apply the force is a little bit different. So that force, so the force here in case number 4, it's not constant. So the direction of that force is always along the path. So in case 4, the direction of the force is constantly changing to follow the path. So in that case, let's call this force 2. Let's call this force 1. A to B by this force F2. Should that be F times L or F2 times L or F2 times SAB? Okay, very similar setup, but depends on how the direction of forces is added and the work calculation is different. Okay, that's weird. Light just went off. Yeah. So here, the correct answer for case number 3 is the work done by that force F1 is just force F1 times the distance. Since that force has constant direction, the direction doesn't change. So the work done by that force, it's independent of that path. It only depends on the starting point and the end point. So in this case, it's independent of path. In this case, only depends on the starting point and end point. So in this is very similar to our gravity force. Now my Apple Pencil has a gravity potential, right? And doesn't matter how I move it, a crazy curve, but the potential change from that gravity only depends on my starting point, which is here, and the end point, which is here. Doesn't matter how I move it in between, because that gravitational force is pointing to a constant direction, right? It never changes directions. It's very similar to this case. In this case, the force is pointing to a constant direction, and that work done by that force doesn't depend on the path, only depends on the starting point and end point. For case number 4, the work done, it's F2 times SAB, because that force is constantly changing its direction. In that case, the work done by that force, it's dependent on the path. Can you think about any other forces that is dependent of path? Okay, if we have this surface, the path doesn't have a smooth surface. If we have a friction coefficient, let's call that mu k. And how about the friction force? It's a work done by friction force independent of path or dependent of path? What is the work done from A to B by that friction force? This room is haunted.
The force of the friction multiplied by the path of it'll be multiplied by the L to this constant.
Okay. Everybody stand up. Why is it so quiet today? Stand up. Wake up and spend 1 minute talk to each other to say, what is the work done by the friction force? What's the direction of friction force? Yeah. And if everything is on the tabletop, we're looking at the top view.
So are we saying that or
Yeah.
the top view?
Yeah, top view.
So that's the top view.
Yeah. Okay. So what do you guys think? Should the work done by the friction force depends on the path? If you think that work done is dependent on the path, raise your hand. Okay. How many of you think it's just the friction force times the length L? It's independent of the path. Raise your hand. No? Okay. In this case, friction force just will change its direction all the time. Friction force, it depends on how that particle is moving. So the friction force, work done by friction force is friction force times SAB. So friction force, it depends on the path. Keep that in mind. We're gonna do a lot of practice, and in your homework, you will have problems like this. All right, now you can all sit down. All right. Okay. Now let's do a practice. We're gonna do an example to practice how to use that 9 steps. So we're going to do example 4B2 on your textbook. Okay, in 4B2, we have a slope. We know the angle is theta. And on the top of slope, we have a block. And with mass m, at the bottom of the block of the slope, we have a spring. So distance from this block m to the spring is d. We know the distance and we know the mass. We also know the surface friction coefficient, which is mu. We know the spring constant, which is k. So we know a couple of things. M equals 5 kilogram. Theta equals 53.13 degrees. D equals 0.75 meters. Mu, in this case, is mu k. Kinetic friction coefficient, it's 0.3. And k, it's a spring constant. In this case, is 1,000 Newton per meter. Also, we know the block M, it's is at rest, so it's not moving at beginning. So we want to find out what is the deflection of the spring when we release the block M. So at beginning, at position 1, that block, it's hold as still, so it's not moving. And if we release it, it will sliding down the slope and will hit the spring. And once it hits the spring will be compressed. We want to find out what is that deflection of the spring. In other words, a change of length of the spring, delta x. Okay. So we can use the 9 steps to solve this problem. And I believe right now you should be very familiar with the first 5 steps. So I will give you 5 minutes, work on the first 5 steps. Then we're gonna work on building tables together. 5 minutes, 5 steps. Remember, make sure you set up, write out step 1, 2, 3, 4, 5, and label each step. Questions?
If you draw a free body diagram.
Good question. In this case, if you read the problem statement, how many masses were given? We're only given one masses, which is that block. That tells you we only care about how that block is moving. So when you draw free body diagrams, how many free body diagrams do you need? Just one for that block. Okay, raise your hand if you're done with the first 5 steps. Give you 1 more minute. Okay. All right. I assume everyone is done with the 5 steps. All right, now let's look at step 6. Let's build the table together. So step 6, you should build a table for kinetic energy. But before you do that, you want to ask yourself, what is position 1 and where is position 2? Because in our kinetic energy, we have that 1, T1, T2. You have to figure out where's position 1, where's position 2. So the initial point is always the position 1. In this case, initial point would be when the block M is holding up there, not moving. That's our initial position. What is our position 2? When it's on the spring, when the spring is compressed to its maximum, right? When the block is hitting the spring and compressed, has a maximum deflection. So that's position 2. Okay, in that case, we know where's position 1, position 2. Now let's think about what is the kinetic energy at position 1, T1. How to calculate kinetic energy? That's 1/2 m v1 square. What is the velocity or speed at position 1? What's the speed at position 1? 0. Why is 0? So I think in most of the problem it says release from rest. When you see that, that's a sign we don't have any speed. So speed at position 1 is 0. How about kinetic energy at position 2? M 1/2 m v2 square. What is the speed at position 2? Do we know that? What's the speed at position 2? When the block hit the spring and compress the spring to its maximum. Can you guys see that? The velocity at position 2 is 0. Can you play a small movie in your brain? When a block is hitting the spring, compress the spring at that one moment, and it will have 0 speed, and right next moment it will be pushed back by the spring, right? So at position 2, V2 is 0. We have 0 kinetic energy. So that's interesting. 0 kinetic energy at the beginning, 0 kinetic energy at position 2. Okay. Are we done with this table? Do we have multiple masses in the system? No. So we're good. We're done with this table. Let's move on to step 7. Build a table for potential energy. Okay. We have two different types of potential energy. Potential energy can come from gravity In that case, what is potential energy from gravity? The equation is just mg times h, right? That's a potential energy. Remember last time we had a discussion? What is the potential energy of that remote control? It depends on where you set up your reference point, right? So before you do step 7 to calculate potential energy, go to the diagram to set up where's your 0 reference point. So in this case, where do you want set up as the 0 reference point on this diagram? Ground? Yeah, you can pick ground. Or you can just pick the starting point as a 0 reference point. Doesn't matter which one, but make sure you define that 0 reference point. Let's all agree that this height, this is our 0 reference point. So if that is our 0 reference point, what is the potential energy at position 1 of that block? What is the potential energy of that block at position 1? Should be mg h1. Let's call this guy h1. What is h1? H1 is not given directly, but we know angle, we know the distance d. We can calculate that h1 equals, that's opposite hypotenuse, that should be sine theta d sine theta. That's your h1. Okay. Now we can go back to this table to finish the calculation here. So equals mg d times sine theta. That's our potential energy at position 1. It's positive because it's above the 0 reference point. Let's make sure that's positive. So positive. Okay, what is the potential energy at position 2? Let's look at here. Position 2, the block will reach the ground level, then we define that's a 0 reference point. So we have 0 potential energy. mgh2, which is just 0. Okay. Question here. Are we done with this table? What else need to be done? Look. Yes. We only done with gravity, gravitational potential energy. We still need to deal with spring. The spring would also have potential energy. What is the equation to calculate spring potential energy? Remember that equation last time we learned? That's 1/2 k delta x squared. But here, make sure you label that's delta x1 since we're talking about position 1. So what is delta x1 at position 1? At position 1, what's the length of that spring? Is it compressed or is it extended, stretched? At position 1, where's position 1? At position 1, the blocks is up there and spring is down there, nothing is in contact. So the spring is in its original length, right? So the delta x1 is 0. There's no deflection in the spring. So here we have 0 at the beginning. But at position 2, it got compressed. And that's delta x2 we're trying to find for this problem. It's 1/2 k delta x2 equals 0. Delta x2 squared. Make sure you add that square. Okay, now we're done. Oops, that's not 0, my bad. This is something we're trying to solve. Okay, now we're done with step 7. Now let's look at step 8, table for forces, table of work. In this case, we have the work done from 1 to 2 from non-conservative forces. What are the non-conservative forces in this plot? From our last lecture, we mentioned most likely we only will see 2 different types of non-conventional forces. One is friction force, another one is external forces. In this, do we have friction force in this case? Yes, we do. There's friction coefficient on that surface. So we have friction, work done from friction. And how to calculate the work done by that friction? It's just friction force times the distance it traveled. In this case, it's just a straight line from 1 to 2. That distance is given as d. And keep in mind, the work done from friction force is always negative. So make sure you add a negative sign. And keep a note here. That's something you should remember. Work done from friction force. It's always negative. Okay, in this problem, we only have one non-conservative force. So that's it for step A. Okay, step 9 is to assemble the work energy equation. That is T2 plus V2 equals T1 plus V1 plus work done from non-conservative force 1 to 2. Look at your table for kinetic energy. T2 equals 0, T1 equal to 0. That's pretty easy. We can plug in T2 and T1. Also plug in what is V2. For V2, we have 2 parts. One's from gravity, another one's from spring. So make sure you add them up. 0 plus 1/2 K delta x2 square equals T1 equals 0 plus V1. V1 has 2 terms as well. If you look at the table, that's mg sine theta times d plus 0. Okay. I have one more term that is work done from non-conservative forces. We know that work is negative F friction force, FF times D. Okay, that's how you assemble the work energy equation. And from that equation, you're able to solve what is delta x2, which is the maximum deflection. Any questions? Okay, one more thing. This problem, what we did here, it's not very accurate because if we look at the potential energy, we assumed at position 2, there's no potential energy because it hits the spring. But if we look closer to this problem, if we draw that at position 2, the spring got compressed. That's your block. And you still have a little bit potential energy. You have a height there, right? So, and if we know the initial length, let's call that initial length of the spring, it's L naught. And the change of length here, it's delta x2. We can use that length and angle to find out what is this H2 here to make it more accurate, to find what is potential energy at position 2. Okay. All right, but this is how we use 9 steps to set up problems. Make sure the tables are very important. Make sure you have all the tables in your homework and in your future exams. Okay, any questions? That's all for today.